Hello, my name is Kevin Mark F. Cruz, and I'm doing a report on optimization. We are going to fence in a rectangular field. If we look at the field from above, the cost of the vertical sides are $10 per feet, the cost of the bottom is $2 per feet, and the cost of the top is $7 per feet. If we have $700, determine the dimension of the field that will maximize the enclosed area. The first step is to do a quick sketch of the problem. We could probably skip the sketch in this case, but that is a really bad habit to get into. Next, we need to set up the constant rate and equation that we are being asked to optimize. 700 equals to 10y plus 2x plus 10y plus 7x equals to 20y plus 9x. Now, let's solve the constant rate for y. Y equals to 35 minus 9 over 20x. Finding the critical points for this should not be too difficult at this point. So here is the work. A prime of x is equals to 35 minus 9 over 10x. 35 minus 9 over 10x equals 0. X is equals to 350 over 9. From this, we can see that the second derivative is always negative and so will always be concave down, and so the single critical point we got in step 4 must be the relative maximum and hence must be the value that gives a maximum area. A prime of x is equals to negative 9 over 10. Now, let's finish the problem by getting the second dimension. Y equals to 35 minus 9 over 20 times 350 over 9 is equals to 35 over 2. The final dimension are x is equals to 315 over 9, y is equals to 35 over 2. We have 45 meters of material to build a box with a square base and no top. Determine the dimension of the box that will maximize the enclosed volume. The first step is to do a quick sketch of the problem. Next, we need to set up the concentrate and equation that we are being asked to optimize. 45 equals LW plus 2 times LH plus 2WH equals W squared plus 2WH plus 2WH equals to W squared plus 4WH. Now, let's solve the concentrate for H. That will allow us to avoid dealing with roots, plus there is only one H in the concentrate, so it will simplify be easier to deal with. Finding the critical points for this should not be too difficult at this point. So here is the work. From this, we can see that the second derivative is always negative, and so will always be concave down, and so the single critical point we got in step 4 must be a relative maximum and hence must be the value that gives a maximum area. B prime of W is equals to negative 6W. We want to build a box whose base length is 6 times the base with the box will enclose 20 per in. The cost of the material of the sides is $3 per in and the cost of the top and the bottom is $15 per in. Determine the dimension of the box that will minimize the costs. The first step is to do a quick sketch of the problem. We are told the volume of the box must be 20 in, and so this is the concentrate. 20 is equal to LWH equals 6W squared A. Now, let's solve the concentrate for H. That will allow us to avoid dealing with roots. H is equal to 10 over 3W squared. Finding the critical points. For this should not be too difficult at this point. Here is the derivatives. The critical point is W is equal to 0 and W is equals to 3 square root of 17 over 18 is equals to 0.7299. From this, we can see that the second derivative is always positive for positive W. Therefore, provided W is positive, will always be concave up, and so the single critical point we got in the step 4 must be a relative minimum and hence the must be the value. Now, let's finish the problem by getting the remaining dimensions. The final dimensions are W is equals to 0.7299 and L is equals to 4.3794 and H is equals to 6.2568. The end!
Created using Powtoon.